All right, I'm Akuru Yahweh Abanwonse. Good evening. Welcome to this series of online lessons. So today I have a tutorial sheet from EMS, and this is basically course on stochastic processes. I'm just going to run you through so that you get the intuition behind what the tutorial sheet is trying to communicate. All right, so you are given a MarKov chain. So I did some problems on MarKov chain in previous videos. If you haven't checked that out, you should. So we're given a MarKov chain written in a stochastic matrix. So remember, a stochastic matrix has the rows summing to 1. And how you read a stochastic matrix is these represent more like the starting points, and these represent the points where you're going in our case. So, but there are some stochastic matrices that are written such that we are reading by columns. So, but in our case, we're starting, and in most books you find these being the initials and these being the endpoints. So starting at 1 and going to 1, we have a probability of 1/2. Starting at 1 and going to 2, that is probability of 0, and so on and so forth. Starting at 3 going to 5, that is a probability. So that is the general idea behind the matrix. Now you're asked to draw the chain. So you're given a Markov matrix, I would call it, and now you're asked to draw a chain. Now to draw the chain, we'll just be considering the states that you have. So we have states 1, 2, 3, 4, 5. And basically I'm just going to say 1, 2, 3, 4, and I'll put 5 here. So the states represent the vertices of the chain. All right, so that those are the vertices. So moving from 1 going to 1, so from 1 going to 1, that is a self loop that has a probability of 1/2. Moving from 1 going to 2, so from 1 to 2 there is nothing, it's 0. Moving from 1 to 3, it's 0, we can't write anything. From 1 to 5, so we are moving from 1 to 5, and that has a probability of 1/2. We come to 2, so moving from 2 to 1, so from 2 to 1 we have a probability of 1/3. Moving from 2 to 2, so looping from 2 to 2, there is a probability of 1/2. Moving from 2 to 3, so 2 to 3, we have a probability of 1/6. Moving from 2 to 0 to 4 is 0, 2 to 5 is 0. Moving from 3 to 1 is 0. Moving from 3 to 2, so we are moving from 3 going to 2. The probability is 1/4. Then moving from 3 going to 3, that's 0, but 3 going to 4, that is 1/2. So from 3 to 4, we have a probability of 1/2. Then 3 to 5, so we are moving from 3 to 5 with a probability of 1/4. Then we come to 4 with everything else. Here is 0, 0, but 4 to 4, there is a self loop from 4 to 4, which has a probability of 1. Then 5 to 1 has a probability of 1. So basically this would be the chain diagram, right? And we can move from chain diagram to the matrix by the same logic, just considering the number of vertices. Those will be your states, and since this is a directed graph, you consider where you're starting from as being this part of the matrix and where you're ending that, and you just map onto that. So that is the first part of the question. Find the communication classes. So communication classes, you can think of it as classes that form a circle over themselves, or if we can find loops, the loops where we can move in a complete circle like that, we can say that is a class. So we can move from there back to there. That is a class. All right. So that is how we're going to find these classes. So the first loop that we have is from this to this. So that is 1. We can move from there to there. That is 1. Okay. Let's see if we can have any other loop. All right. So let me label this so I can move from there to there. That is 1 loop. Is there any way that I can move in a circle? Right? I can move from here to here. That is a loop. And is there like a bigger loop where maybe I move from here to there? No. All right. So, and we have this one by itself. So these are the only loops that we have. All right. So in this case, the classes will just be those that are the vertices that are forming a loop. So that is 1, 5 and 2, 3 and 4. So these are the classes that we have. Or maybe let me just give an example here so that you get a feel of the issue of classes. So maybe you have 1, 2, 3, 4, like that. So then you have like this, like that, that. Okay. Say you have something like that. So you have to look for a loop. So you see that there is a loop here. So this would be one class. Okay, and this one would be by itself. So the classes would be the first one in this case would be 1. Then the other ones will be 2, 3, 4. So that would be the classes. So that is the general idea on the classes. So in our case, these are the classes 1, 5, 2, 3, and 4. Now, is this MarKov chain irreducible? Okay, so is it irreducible? The answer is no. Okay, why? You count the number of classes. If number of classes is more than 1, then it is irreducible. The other way you can think of irreducibility is if you can move from the point A and visit all the other nodes. All right, then we can say the MarKov chain is irreducible. So in this case, since we have many classes, so when you move from A to 5, you're pretty much stuck here. You can move around this and so on and so forth. So this is irreducible. So starting at A, we cannot move everywhere. All right. So since we have many classes, this is not irreducible. So no, because we have more than one class. All right. Okay, we go to exercise 2. Consider a MarKov chain with a transition matrix. So this is the transition matrix that you've been given. Obtain the closed form of Pn. So what they want you to do is move from P to the power 1, P to the power 2, P to the power 3, all the way, and you find the general form of P to the power n, and that will be the closed form of P to the power n. So we can start by we know what P to the power 1 is. It's just this. Then P to the power 2 is multiplying the matrix by itself. So we have 1 over 2, 0, 1 over 2, 1, multiplied by 1 over 2, 0. So let me put it down a bit. Okay, I'll just write it here. 1 over 2, 1. All right, so we multiply this matrix with that to find p to the power 2. Then we also find p to the power 3, which is p to the power 2 times p. And when we do that, maybe up to p to the power 3, because we want to observe the trend. Let me just do that very quickly. All right, so when we find p squared, it should give us something like that. So this times that, 1/4, and so on and so forth. We go to p, so this is like we have p squared, which is 1/4, 0, 3/4, 1, multiplied by p, which is 1/2, 0, 1/2, 1. So let's multiply that out again and see if we have a trend. All right, so that is what we're getting. So we can line them up. So p to the power 1, we have 1/2, 1/2, 0, 1, and so on and so forth. So now when we check this one, the first entry here, we see that in the next step, it goes from 2 to 4, and from 4 to 8. Okay, meaning that there is some form of squaring, okay, or raising to the power. So from this can just be 1/2 to the power n. So when n is 0, we're going to have 2. When n is, okay, we can say when n is 1, because since the p to the power 1 is this one, so when n is 1, we're going to have 1/2 to the power 1. When n is 2, we're going to have 2 to the power 2, which is 4. When n is 3, we're going to have this matrix. Then here we see the trend. It's like the one on top is like 1 less the one on the bottom. So we see the one on top is 1 less the one on the bottom. The one on top is 1 less the one on the bottom. And we check that the one at the bottom is actually having the same denominator as this one. So we know that at the bottom we have some form of 2 to the power n. And at the top, we're just going to say 2 to the power n minus 1, because we are 1 less from the denominator. Then here we are seeing that this continues to be 0, this will continue to be 1. So that will be the form of p to the power n. Right, so let me erase everything and write like p to the power n. All right, so we have the general form of p to the power n. Now we're asked to exhibit this sum, so we're just introducing summation from n equals to 0 to infinity of p to the power n. This will be summing each of these, so it will be the sum of 1/2 to the n from 0 and so on and so forth. Let me just write it like that. We have the sum. We can break this sum out as 1 minus the sum. Actually, so this goes to infinity, starting from 0, 1/2 to the n. Then we have the sum of zeros will just be 0, and we have the sum of ones to infinity. So we can simply calculate what each of these will be. So we see that for the first one, this is a geometric series which converges for z modulus less than 1. So this converges to 1/1 minus z, something like that. So this converges to that. So we can really find the sum of this by using this formula. So we see that 1/2 is actually less than 1, so we can use the geometric sum. So this will just be equal to 1/1 minus, what we have here is the same thing as 1/2 everything raised to the power n. So this is our z, so this is what we put over here, and we put over here, and this will simplify to 2. So meaning that this converges to 2, and we're going to have 0 there, this diverges because you're summing ones to infinity. So summing ones to infinity is like summing the, I don't know what you're summing. You're summing all the infinity points. Then converging, this one converges and this one diverges. Summing them together, you're going to have divergence. Then here we're going to have infinity. So here we're just putting divergence as infinity by virtue of having this sum and this going to infinity. Okay, since this goes to infinity, summing to that, we're assuming we're at infinity. All right, so that is what we're going to have for question 2. Now question 3, what does this say about the recursion transients of states? All right, so for the recursion, you should know that recursion is where you're going in a loop infinitely many times. So if the sum of some an goes to infinity, meaning that we are looping, that is recursion. So where we have infinity, we have some form of recursion, right? So this is, okay, we can say this is state. We can put the states like that if I were to simplify, though not really, but we could think of it as moving from 1 to 2. We're going to have a recursive relationship. Moving from 2 to 2, we're going to have a recursive relationship. And moving from 1 to 1, when you go from 1 to 1, you stay at 1. Basically, from 2 to 1, you stay at 2. So this is a transient case where the sum of an is less than infinity. So this is the comment that you would give on this question here. So we move on. All right, to make the video short, I'll end here. Then in part 2, I'll do this question. So check out for that. Have a great evening. See you in part 2.